Okay, so good morning, everybody. So my second favorite group is the group of diffeomorphisms of a compact manifold. So basically what I want to do today is a huge subject. I have to choose one or two topics. So I decided to select two examples of two open questions. So before I do that, I have to recall that in the 70s, William Thurston and John Mather proved the following theorem. If you consider a compact manifold M, and the group, the connected component of the identity of the group of diffeomorphisms of M, they proved that this is a simple group. This is a highly non-trivial theorem. However, they proved it in most cases. There is a case which is still open for 40 years, and that I want to mention today. Of course, when I say diffeomorphism, I should explain what degree of differentiability I want. And they proved it under the assumption of if R is not equal to the dimension of M plus 1. Incredible. In particular, the very naive question of the simplicity of the group of diffeomorphisms of class C2 of the circle, let's say orientation preserving, is completely open. Is this group simple? And this is my first question of today. I can tell you that I discussed that with John Mather. He told me that he spent years on this question. So we need new ideas. We need young people having new ideas. Let me explain a very beautiful idea from Mather, showing that this question might be very subtle. I'm going to show you that there's a group which is very similar to this one, which is not simple. The group I want to discuss has been studied by many people. It is denoted by diff plus S1, and here 1 plus VB, BV in English. BV means bounded variation. So this is the group of diffeomorphisms of the circle, orientation preserving. Which are C1. So the derivative is a continuous function, but you want the log of this derivative to be a function of bounded variation. So you see, it's a bit better than C1 and a bit lower than C2. This is a fascinating group, which is not this is not artificial group, it's a very fundamental group in dynamical systems. This is the right category in which the so-called Danjois theorem is true. This is the theorem, this is a beautiful group which has a significance. It's not just from the mind of Mather. So let me show you the theorem of Mather, that this group is not simple. So here's the theorem of Mather. There is a non-trivial homomorphism, let me call it Mather, from this group to the real numbers. Therefore, this group is non-simple because it has a non-trivial homomorphism onto the reals, and the kernel is a non-trivial normal subgroup. So let me prove that. You see, it's very, very clever. I like this. Mather wrote many papers, maybe 10 papers, with the same title. It's called Commutators and Diffeomorphisms. 1, Commutators and Diffeomorphisms. 2, and 2, 10. And most of them are very long papers, like 100 pages of computations. And one of these papers contains only the theorem. It's 2 pages. This is the only paper I understood. So let me explain that. If you have 2 diffeomorphisms of the circle, you can compute derivative of the composition by the chain rule. If you put a log in front of it, you get this. Now assume that the derivative log of f prime is a function with bounded variation. Now I need to make a very short and quick reminder about functions of bounded variation. Functions with bounded variations are essentially the same thing as measures on the line. If you have a function u on the line, let's say on the circle, you could try to define a measure by defining the measure of some open interval by measure of AB is f of b if u of b minus u of a. So this is something which is additive on intervals, and you want to know if you can extend it to the sigma algebra of Borel sets. And the condition of being bounded variation is exactly this one. So a measure is the same thing as a function with bounded variation. So I can look at this equality as an equality between measures. This measure is equal to this measure plus this measure. I can put it this way. So let me now define the Mather invariant. Take a diffeomorphism f, take log of f prime. This is a measure on the circle. Now you may remember that a measure can be decomposed in a measure which is absolutely continuous with respect to the Lebesgue measure plus some other measure which is orthogonal to the Lebesgue measure. There is a canonical decomposition. Any measure can be split in 2 parts. One absolutely continuous and the other one is singular. Okay, so let me take the singular part of it. So this means log of f prime is a measure. I take the singular part of it. And this is a measure. I take the mass of it on the circle, the total mass. I integrate the singular part of log of f prime on the circle. Now, because of this equality, this measure is this measure plus this measure. The singular part is the singular part plus the singular part. The total mass is the total mass plus the total mass. Therefore, this is a group homomorphism. So, the theorem is proved. 2 pages. Well, I have to check that this is on 2. So what could be an example to show it's on 2? Well, you take a piecewise linear map. For, you can find examples on which this map is non-trivial. Why it's not okay on C2? Yes? You know, this is an equality between 3 measures. This measure is equal to this measure plus this measure. And the important point is that the decomposition of a measure in a sum as a sum of an absolutely continuous plus singular is additive. That's it. Okay? Now, if you take a C2 diffeomorphism, log f prime is a function, continuous function. Now, what can you do with that? Nothing. So if you try to prove something like diff2 of S1 is not simple, well, you should be clever enough to give some coherent definition of the integral of such a function, of such a measure. It's not a measure. Okay? By the way, there is a theorem claiming that if you want to show that diff2 S1 is not simple, the only way is to prove that there is a homomorphism onto some abelian group. This is a general fact. Okay, so this is question number 1. I have 25 minutes. I used 12 minutes for the first one. So let me go for the second one. In the 70s, Calabi showed that the group of diffeomorphisms of the disk, which are the identity on the boundary and with respect the area form, is not simple. So this is the group, again, of all diffeomorphisms of a disk respecting area identity on the boundary. And to show that this group is not simple, he explicitly constructed a homomorphism onto R. Here it's of class C1. So here's how Calabi constructed his homomorphism. That's like magic. You take a diffeomorphism phi of the disk respecting the area. So you know that the form dx dy is preserved. This is definition of preserving the area. Well, now you look at the form x dy. Of course, it is not preserved. There is no reason for this to be equal to 0, but the differential of that is 0. So this is a one form which is closed on the disk. Being closed, it is exact. This is the differential of some function h. This function h is well defined up to some additive constant. So choose it in such a way that h on the boundary is 0. And now you define the invariant of Calabi to be the average value of h on the disk. And this is an exercise for you, really an exercise, to prove that this is a group homomorphism from diff D2 respecting the area and the boundary onto the real numbers. A few years later, Banyaga proved that the kernel of this homomorphism is a simple group. Now let me go to the open question. What about homeomorphisms? This is a little bit like, you know, this Thomson group for which there is a proof of amenability every 6 months and a proof of non-amenability every 6 months, all of them being wrong. The question I'm going to ask is similar. It has many wrong proofs. The question is this. Look at the group of homeomorphisms of the disk, identity on the boundary respecting area. Is it simple? So let me try to explain how I tried to prove it. I mean, I tried to prove it's not simple. I couldn't do it. But nevertheless, let me explain the idea, and you will see there is some kind of similarity with the first question I was asking about diff of the circle. First of all, nobody understands a word about this definition. Just computations. What is the exact meaning of this number? So let me tell you a definition. an interpretation of Calabi that I found with Gambodo. And that's also a very interesting story. I found this interpretation with Gambodo. I lectured about it several times, including in my department, including in front of my colleague Albert Fati. And we published a paper containing this interpretation. And after the paper was published, Fati told me, now I remember, it was in my PhD. And that's true. I mean, part of my paper is included in the PhD of Fati. So this is really not Gambodo, not me, but Fati. So here's the idea. You consider a diffeomorphism of the disk, identity on boundary, respecting area. You take 2 points in the disk, x and y, and you connect phi to the identity by some isotopy phi t. So phi 0 is the identity, and phi 1 is phi. Now you play the following game. Take x, y, and you look at the motion of these 2 points during time t. So this is phi t of x, phi t of y. And this is phi of y, phi of x. And now you look at the vector connecting phi t of x to phi t of y. So it's a vector in the disk, and therefore in the plane, which is somehow moving in time. And you look at what's happening between time 0 and 1. You have a vector rotating, and finally you count the total amount of rotation. So I call angular the angle phi of xy is the amount of rotation, the angle of rotation of the vector xy under this isotopy phi t. It's a number. It tells you how much of rotation you have. Okay, now you look at the average value of this over all pairs of points x and y. So it's the average value of rotation of the diffeomorphism. And we proved, or better to say, Fati proved, that this is equal to Calabi. So really, Calabi tells you about the amount of rotation contained in a diffeomorphism. It's something like a rotation number. It tells you if the diffeomorphism is mostly rotating right or mostly rotating left. So when we discovered that, I was very happy with that, because I said to myself, okay, this definition is not using any kind of smoothness for phi. If phi is a homomorphism, not differentiable, I can also look at this path. I can also look at the rotation from x to y. I can also take the average value over the disk, and this gives me a number, and this will produce a homomorphism from homeo D2, boundary D2 area into R. But the problem is, what is the problem? Yes, the problem is that if the map is not smooth, it's a homeomorphism, it could be very complicated locally, and there could be a very infinite amount of twists. If 2 points are very close together, it could be very, very twisted. So this function, to be true is not a function on D2 cross D2, is a function on D2 cross D2 minus the diagonal. So it's a function which is not defined everywhere. When phi is smooth, this is a bounded function. But when phi is not smooth, it's a continuous function, which might be not bounded, and even worse, it might be not integrable. So when phi is homeomorphism, This makes no sense. So this is, oh, I'm almost done. So the challenge for you would be to give a meaning to that. You know, in mathematics, some divergent series, you can make them convergent using tricks. So the question is, can you make a sense, can you give a meaning to this integral in such a way that this provides a homomorphism from homeomorphisms to the reals? So I must add that the expert on the subject, who in particular proved many times many wrong proofs, the expert on the subject claims that the group is simple. So most experts do not agree with me, and most experts believe that Homeo is a simple group, unlike diffeos. I'm done. Thank you.
In the situation of the Mather-Thurston theorem, is there always a quasimorphism, non-trivial, on that group?
I believe so. It seems to me that you know, the class. Well, I'm not sure. You know, the classical fact that any diffeomorphism of the circle is a product of two commutators uses some analysis, and we should check if this analysis is valid in the C1 plus bounded variation category. This I'm not sure, but I would be confident it should be true, but I don't know. That's a good question. That's a good question.
More questions from the audience? So if not, let's thank the speaker again.